Thank you for not all moving away. I have to admit I have only one video, so I might be a little bit in the wrong place. When I was coming today, somebody told me if you don't have videos, you're in the wrong place. So, this is somewhat the effort to tell you a lot of things in a very short time, so it will be very high level. But I'm very open to questions you have afterwards. We will not go down into detail. And maybe, because I guess most of you are not academic researchers, you will be surprised what we actually do at the moment in the real-time strategy area. So the talk is about multi-objective and fuzzy techniques for balancing and improving. It's not 100% about balancing. We are not that far yet. We are working on smaller things now, but we want to get to this. And multi-objective and fuzzy techniques obviously are not really related, but I will talk in short about them before I tell you how we apply that. So that is the outline. I will first start with a state of research, of academic research on strategy games, especially RTS. I will tell you a little bit about the ongoing STARCRAFT competitions and the results we got. Then comes the fuzzy logic part, very high level. Actually, I'm not really a fuzzy logic researcher. I apply that, so I guess you can do that as well. If you want the details, you have to look into the papers or read the books. So don't rely that I can tell you all the details on that. Then I go to adaptive strategy selection, applying the fuzzy stuff. And then comes the multi-objective part. Actually, I am a researcher in multi-objective, so I should know a little bit more about that. Then I'll tell you how we apply that concerning the assessment of STARCRAFT strategies, and then some works. So this is, so to say, the stuff I know that is going on in RTS research at the moment or in the last years. We basically work mostly on STARCRAFT 1, which is very, very old, I agree. The point is we don't have many interfaces to new games, so we have to take what is there. Actually, I have been discussing that several times with several people from industry, and they are relatively reluctant to give us access to their new stuff. But that's okay, I think. Basically, if it works in STARCRAFT 1, it should also do well in other games. There's a third-party hack that makes the game accessible, you know. It's not by Blizzard, but anyway, it's not important here how we do it. Yeah, what we do is actually, let's say, compose bots, AI players, out of different components, and the most pressing problem we have is not to make many mistakes or not to build too many mistakes in the bots, because players and also other bots can exploit them and then win the game easily. So there are a lot of things here on the list that have been done in the last years and are currently done. It's not the full picture, I guess. It's the one that I know. There's, for example, some research in scouting behaviors, influence maps with flocking behaviors, a little bit like the Scout stuff we had before. Fuzzy strategy selection, I will talk about this. Multi-objective assessment of build orders, I will also talk about this a little bit. Technical modeling using a third-party programmed free tool, STARCRAFT, and things like mixed initiative making, that is more or less procedural content generation. Okay, about the competitions. Well, the competitions run since 2010 or 2011. I mean, there are other STARCRAFT competitions, but I don't know these too well, so I report about the ones I know that are running at scientific conferences for years now. It's just two-player games, two bots against each other. Mostly very large tournaments, like with 4,000 games or things like that. There's even a software that runs games automatically. On 10 maps, and I think the setup hasn't really changed since years. The original idea was at one of the conferences to use known maps so that the bots or the AI players can adapt, and for the other conference to use unknown maps, but we found out that it doesn't make too much of a difference. Actually, it's the results are more or less the same. Yeah, what else should I say? Since 2012, there's persistent storage. So after the game, you can log things and save them somewhere into a file and read them afterwards for if you meet the same enemy again or the same opponent bot again, then you can, for instance, look up the tactics you used or some things like that, whatever you want to store. So that's possible, but it's not used too much, I would say, at the moment. So at a glance, some competition results, the bots have been getting better. At one of the conferences, I know that they have been playing with a human against the winning bot, and the human was always winning. So I think in the first year they tried a former professional player, he was always winning, and then they tried I think gold or silver league player, he was also always winning, so they reduced the quality of the human player, but still humans are almost always able to beat the winning bots. So I guess there's still some work to do. An interesting example here, the graph means just the bots over here, that are the 10 bots we had in 2013, I think, in the competition. So this is the graph on small maps, this is the graph on big maps, and the bots over here have a probability to beat these bots. An interesting example is that this IU bot, most of these bots are Protoss. If you know STARCRAFT, there are 3 factions, Protoss, Terran, Zerg. For example, there is a difference here between here and here. So in the small maps, some bots are able to beat other bots reliably. On the large maps, it doesn't work anymore. So map sizes, as many different other factors, have some influence, but we are far from actually understanding why this is the case, or let's say making the bots as flexible as they can handle everything. The other thing is, I just told you the bots are not very flexible. That's actually true. They don't adapt very well to the opponent's strategy. In fact, this picture, I think it's data from 2012 from the 8 conference competition. Just to show you, there are a lot of single colored blocks here, and this means that regardless of what the opponent is like, they play the same strategy. They don't try to adapt the strategy in any way. They don't switch the strategy within the game, and they don't try other strategies if they, for example, see an opponent, Zerg player or Protoss player or Terran player. So there are bots that choose different strategies if they see, for example, a Terran player, but this is something we have to work on, that bots have to be flexible, adapt the strategy, and select the right strategy at the beginning already if they play against different bots. So now comes the fuzzy part. As I told you, I'm not really a fuzzy logic researcher, so I probably don't know much more than you do, but what I know is that fuzzy logic is good for, let's say, as I put it here, computing with adjectives. So fuzzy logic is about an unsharp logic. You can say that something has some property to a certain extent, like here in the example where we have the player army size, and you can say that, for instance, if 200, like, which is the PopCap for StarCraft 1, at 200 it's clear that an army is large, at 0 it's clear that an army is small, and there are all kinds of army sizes in between, and why should you do that in that direction, compute with adjectives? Because actually if you ask players how they act, how they try to define their strategies, their tactics, they tell you something like, if the army is large, I do that, or if my army is small, then I do that. They don't tell you, if my army has exactly 15 units, then I do that, because that's not how humans think. And that's an interesting example to apply fuzzy logic. So we used that actually 2 years ago for implementing a real-time strategy switch. So to make the bot able to react on what he actually sees in the game, because there's a lot of information coming in that can be used. And then to make a fuzzy logic-based strategy selection. Of course, you have to have strategies for that you can choose, and these strategies have to be defined by human players, or let's say you have to know how human players would do the strategy, and then you can somehow implement them into the AI. The inputs you have available are, for example, scouting data, general info like the ongoing time and so on, may be important because you can't start a rush at 10 minutes playing time. And the units you have seen from combat or whatsoever. There's a lot of data available. And then you can try to apply rules, and rules could look like, I gave the example here, a human player saying, if I see many opponent air units, I build several anti-air units. So it's a very simple rule. Of course, you need a lot of these rules to define a proper reaction. And then what the fuzzy logic is actually doing is just selecting one of these defined strategies, well, by just using all these rules and then, so to say, select the one that applies best. That's the very simple idea. So of course, what you need to apply that is a selection of strategies. You need then a number of rules. For that you need an expert, as I already said, a human that can somehow give you some idea of how strategies should be applied and when strategies should be applied. Then you feed the current input into your rules. The fuzzy system then comes up with a usefulness value, and then you take the strategy with the highest value. All very simple. Okay, and we actually implemented that into an existing bot, and well, now you are almost at the point where the video comes, where it shows that this graphic basically tells you that actually different opponents, for different opponents, and these pictures were the opponents, the Terran AI and the Protoss AI over here, the built-in, I guess, and actually the system reacts differently. So the percentage numbers is the overall time that was spent in one specific strategy. So now I'll try to start the video, and it actually shows that the Protoss player is starting with the Dark Templar. Dark Templar is an invisible unit, unless there are specific units that can see the Dark Templar. So it's starting to more or less execute all the different units from the enemy coming in. Because it's not visible, the enemy can't do anything about it. And then at a certain point, there's an overlord coming in. Now there's the overlord, this big thing here. So if the overlord is in the range of the units, then the Dark Templars are actually visible. And now what the Protoss is doing is changing the strategy to a ground attack, because it doesn't make sense anymore to build this very expensive invisible units if they are visible because the overload is there. So that's what I tried to show you. It actually makes sense to switch the strategy within the game, and it's not difficult. There are only a few rules, and we had, I think, 5 basic strategies implemented, and of these 5, only 2 got very often used, and these were the ones you already just saw in the video and in the graphs before. That was the Dark Templar strategy and the ground attack strategy. Usually the Protoss player started with the Dark Templar and then switched to the ground attack when the overlords came in, or comparable units. Of course, you can also use this for other bots. What do you need to do? In principle, you can also use it for other games, of course, other real-time strategy games. Of course, you need fuzzy rules. You need an interface where you can get information from, like the BW API interface we use. And you can more or less use a basic fuzzy machine. There's nothing specific about it. It can be a fuzzy library you can get off the shelf. And then, well, in our case, we need to plug in the strategy somewhere. So if we use existing AIs, we need effectors. We need to be able to tell the AI, do that now, or do that now. So that's basically, that was our problem in this case, and we only solved it by getting one of the team members on board who actually provided a bot that was already working, so he could tell us where to switch the strategies. Okay. Now for something completely different, so that was a rush through the fuzzy logic stuff, multi-objective optimization. I don't know if you're familiar with multi-objective optimization, but it basically means that you try to solve two or more problems at once. Two you can visualize better, so I used a two-dimensional example here. You may have one target here, and usually we think of, in Europe we usually use minimization. In America they usually use maximization, so for us the ideal point is here, but it's not reachable. So this is just an example. You have different solutions here. This is the second objective, so it should be as small as possible, and this one should be as small as possible as well, but it's not possible to have both at the same time. So what you get is a number of ideal solutions, a so-called Pareto front, and you have to, if you are sure that these cannot be improved any further, you can just choose any of these. They are ideal compromises, so they are optimal in some sense, and what you take depends on you, I mean on your preferences, on other factors. And there are a number of optimization algorithms that do that. The ones I know are all evolutionary optimization algorithms like NSGA2, maybe you have heard of it. It's very well known as LMS, EMOA, and there are pretty many nowadays. So that's the basic idea of multi-objective optimization, and the important thing is you get a set back. There's not one ideal solution, you get a set of compromises, and after the optimization process you have to choose from this set according to your knowledge or to preferences, whatever. The multi-objective strategy assessment works like this, or we did it like this. For a fixed number of units of a single type, of course it would be good to have also mixed units, but that makes it even more complicated, so we started with single type unit groups. We tried to assess or to compute the quickest build order possible. Then we have a number of build orders, and then from these we select the non-dominated points, and the non-dominated points are these points on the Pareto front, so the solutions that are good in both directions. And in our case, non-dominated, or the objectives, means they should be good in the sense of having a lot of military power and have a lot of economic power. There's also a third objective in the back, that's the time, so it shouldn't take too long, of course, to compute the solution, to actually build the units. But to give you an example, what we got out for STARCRAFT 2. For STARCRAFT 2, we have a tool that computes that optimal build order heuristically, so we are not sure that it's actually the optimal build order, but we are pretty sure that's very good already. So this is an example for Zerglings. Very simple, the most simple military Zerg units you can have. And what you can see here is the gray bars here are the number of drones that are built, so the workforce. And this is the number of Zerglings, so the military force. And you can see some interesting points here. Of course, you can start somewhere, but actually it doesn't make too much sense to run or make a rush with two Zerglings that probably wouldn't cause any damage to the enemy, or very little damage. Although you can do it very quickly. Time is going up, of course, and then at some point you have this solution that is 20 Zerglings, and you have a switch here in the number of drones that are actually produced in the optimal build order. These points we call non-dominated, or on the Pareto front, because this point is better in the direction military force and better in the economic power, where time goes to this direction. So it takes, of course, much longer to build these 20 units than the 2. So these points are very interesting, and if you, for example, build only 18 Zerglings with the optimal build order, you are a little bit faster, not too much, but you have very little economic power. So if the rush fails, you don't have any more units in the back. If you take this solution, you have 20 Zerglings, not much more, so the military force is almost the same, but you have a lot of economic power in the back. So rebuilding units should be a lot quicker. So the software we used for actually obtaining the optimal build orders, I hope they are more or less optimal because it's heuristic, as I told you, is called Illusion Chamber. We used that one because we can use it in batch mode. It started from the console, let it run 100 times or things like that. There's also another software, I think it's called SC Fusion, but we could not automatize that, and that's a very common problem in research. We cannot start, if we want to make, let's say, 1,000 runs, we cannot start them manually by pressing a key. That's not possible. We have to somehow automatize that. So I think the details on that are not too important, just for you to know that we ran that a lot of times to be sure that the results are relatively good. This is an example build order. Actually, it's a build order for the 7 ROACH rush, or the best one we obtained. I think it's near optimal. From that picture, you can also see why the 7 ROACH rush is actually very good. I don't recall in which year, I think it was 2011 or so, somebody came up with a strategy. I think it was first 5 ROACH rush, and then somebody came up with the 7 ROACH rush that was actually even better. And you can see here why it is so good. Because if you look here, the workforce you have obtained when building 7 ROACHs is much, much better, much higher. And between these 2 points, there's only very little time. I think it's about 15 seconds, so or 20 seconds or so. You spend 20 seconds more, get 2 ROACHs more, and you have a lot of economic power. So the corresponding line is this one, the corresponding bar. You can see that this is very high. And we believe that this is actually the reason why the 7 ROACH rush was so successful, because if you have an optimal build order and you build your 7 ROACHs and attack, you still have a lot of workforce in the back to rebuild your units, which makes it much easier to react if the rush fails. So of course, as one of the reviews, that was actually a paper some years ago, 2 years ago I think, and one of the reviewers told us, well, you can apply that for almost any RTS game. Yes, in principle, yes, sure. We need a simulator, an optimization tool that actually computes these optimal build orders. Once we have that, it could be very helpful in the design phase already to help the designer, because the strategies that come out there, the Pareto optimized or Pareto front strategies, they are probably the ones that the players will once find when they explore the search space on different strategies. Then at some point they will probably come up with these strategies because they are very strong, because they are strong in a military and in an economic sense. Here. The open problem is how to deal with the possible mixed groups. I showed you 2 pictures only. We have lots more, but only, with one exception, it's only single unit groups. So there are a lot of possibilities, of course, to mix the groups, and it will take a lot of time to compute all the ideal solutions for that. But we didn't deal with that because it takes already some time to compute the optimal build orders for all the single unit solutions. How do we get that into balancing? Well, that would be actually the next step. We can now play with the parameters. If we know what strategies the players will come up with, because they regard them as strong, we could, for instance, change the different unit types or the unit properties. For example, we could also increase the build time of a unit, and then we restart the optimization algorithm and detect different diverse solutions. There's an interesting software, as an example, STARCRAFT, that simulates StarCraft 1 battles. It's been programmed by David Churchill. It's completely free. And this is very often used for balancing like problems. You can, for example, put 2 completely different forces in and let them just play out and see what happens. And if you connect that with the thing I've just shown you, that you know that players will probably come up with 7 ROACHs or things like these, then you can try to rebalance things, to rebalance the unit properties. So that's almost it. There are a lot of things I would like to investigate, or people start to investigate in the next years. I would like to show you. That's on the left half of the picture. The right half you already saw. For example, there are things like shadow bots. What always annoys me is if you have to be away from keyboard for some minutes, then you probably you're probably annihilated until you come back. If you have to go to the toilet, nobody can play for you in this. Or if you are in the team, even worse, and you use your network connection, then nobody takes over. I would imagine that a shadow bot could do this, that actually learns how to play like the human that played before. Then there's automated procedural content generation and balancing, very interesting. Embodiment, realistic characters. By that I mean that the opponents in RTS games should be more visible to the user, more present. And then an assistive AI that actually learns what the player needs. For example, in STARCRAFT 2, the AI does a lot of things by itself. The assistive AI, like for example harvesting. Harvesting is more or less done by the AI itself. In STARCRAFT 1, you had to control that as a player. Some players like that, some players don't. So for players like me who concentrate on the macro management, it's interesting to have this support. For other players, it's annoying. They would rather like to have it all handled by themselves. And it should be possible that the AI learns what the player actually needs. At the moment, I don't see that, but I don't know everything. Maybe in some games it's already existing. It would be interesting to have good methods for that, how to implement that in real-time strategy games. And then a few words about industry-academic collaboration. I also told you that we would like to do a lot of more research on new games, on existing games. Not necessarily the newest versions, but we have the problems that many games are not automizable. That we cannot do, let's say, 100 runs with this configuration and see what comes out. We cannot click 100 times and look what the result on the screen is displayed. It would be interesting. Some people tell me it's a lot of effort. Yeah, I know. It is a lot of effort, but I think there's already also something that you get back because once things are automizable, we can apply a lot of different techniques, a lot of algorithms, and I think it's also interesting for the industry connection to get some interesting results back. Some results you don't get via manual testing, probably. So this is basically it. This is only a summary of what I already told you. The takeaway, there's quite a lot of research on RTS, but it's basically on STARCRAFT 1 because we don't have any other platform. The current RTS bots are still far away from being good, even if you are not a good player. And fuzzy logic and multi-objective are some interesting tools to apply in several contexts. And what we need to foster research together with industry is some interface so that we can automatically play the games or play hundreds or thousands of games in different configurations. Thank you.